Welcome to Daily Papers, the podcast where we break down fascinating new research. Today, we're looking at a paper that tries to solve one of the biggest tug-of-wars in scientific modeling.
That's right. For a long time, scientists have had two main tools in their modeling toolkit, and they're almost opposites. On one side, you have what are called mechanistic models.
Think of these like a detailed recipe or the blueprints for a machine. They're built on established scientific theories and equations. If you're modeling a chemical reaction, you use the laws of chemistry. If you're modeling a planetary orbit, you use the laws of physics. The great thing about them is that you know exactly what's going on inside. They're transparent.
But the problem is, the real world is messy. It doesn't always follow the simple recipe. These models can break down when they face unexpected noise or factors they weren't designed to handle.
So on the other side of this tug-of-war, you have machine learning models, or AI. These aren't based on theories or equations. They are data-driven. You feed them a massive amount of data, and they learn to spot complex patterns on their own.
The upside is their flexibility. They can handle that real-world messiness. But the huge downside is that they are often a black box. We know they work, but we don't always know how they work. And they need enormous amounts of high-quality labeled data, which in science can be very hard to come by.
So you have this dilemma. One type of model is easy to understand, but too rigid. The other is flexible, but is a black box that needs tons of data. This paper asks, what if we could build a bridge between them?
And the bridge they've built is called a simulation-grounded neural network, or SGNN for short. The name really tells you everything. It's a neural network, the AI part, that is grounded in simulations.
This is the core idea. Instead of training the AI on messy, incomplete real-world data, the researchers first create a massive virtual library of simulated data.
Imagine you want to build an AI that understands epidemics. Before you ever show it data from a real outbreak, you use computers to create millions of practice epidemics. You can simulate everything: fast-spreading viruses, slow ones, viruses with long incubation periods, outbreaks in big cities, outbreaks on small islands.
And for every single one of these practice runs, you know the absolute ground truth. You know exactly how infectious the virus is, how many people have it but show no symptoms, everything. You have perfect information. This becomes the AI's training academy.
By learning from this huge and diverse set of perfect examples, the AI doesn't just memorize what an outbreak looks like, it learns the fundamental mechanisms and principles of how diseases spread. It learns the theory.
Okay, so that's the theory. The question is, does it actually work in the real world? The researchers tested it on one of the toughest challenges imaginable, forecasting COVID-19 deaths in the early days of the pandemic.
This is a crucial point. The SGNN model they used had never seen a single piece of real COVID-19 data. It was trained only on those simulated epidemics we talked about. They then gave it the early noisy data from US states and asked it to forecast what would happen next.
The results are staggering. Their model nearly tripled the forecasting skill of the median model used by the CDC's Forecast Hub. It was even more accurate than the single best-performing model in the hub.
And they didn't stop there. To really test its flexibility, they threw it a curveball: dengue fever. Dengue is a completely different type of disease. It's spread by mosquitoes, not from person to person like the viruses in its training simulations.
You'd expect it to fail completely, but it didn't. The STNN, with zero training on anything like dengue, still made forecasts that were 24% more accurate than standard statistical models. This suggests it learned something universal about the dynamics of how things spread.
But maybe the most powerful application is its ability to infer things we can't see. For example, a key number in any epidemic is the R0 value, or R0. It tells you the average number of people that one sick person will go on to infect.
Right, and you can't measure R0 directly. You'd have to estimate it from the data, which is really hard to do when the data is sparse and noisy like it was at the start of COVID. Early estimates for New York City were all over the place, and generally too low.
But the SGNN, because it was trained on simulations where it always knew the true R0, could look at that same messy early data from New York City and infer a much higher and, as we now know, much more accurate R0 value. It could see the hidden truth behind the noisy numbers.
This is all incredibly impressive, but it brings us back to the black box problem. If the AI is this smart, can we understand why it's making these predictions?
We can, and this is the other brilliant part of the paper. They developed a new form of interpretability they call back-to-simulation attribution.
So when the SGNN makes a forecast for, say, Michigan's COVID data, you can essentially ask the AI, In your entire library of simulations, what does this situation in Michigan remind you of?
And the model points you to the specific simulations in its training data that it thinks are the most similar. And because we have all the ground truth data for those simulations, the population size, the fatality rate, the percentage of asymptomatic cases, we get a window directly into the model's reasoning.
It's like the AI is showing its work. It's not just giving an answer, it's telling you what kind of scenario it thinks is unfolding, based on its vast experience from the simulations. It's no longer a black box.
Exactly. This SGNN approach transforms simulations from something we use to test a hypothesis into a powerful source of supervision to teach an AI.
It successfully bridges that gap between the two worlds of scientific modeling. You get the flexibility and power of deep learning, combined with the theoretical grounding and interpretability of a classic mechanistic model. It's a tool that's not just more accurate, but more robust and more trustworthy.